The last section here is about this thing called entropy. Everything tends to be going towards more disorder. The greater the disorder, the greater the entropy. And it's a basic rule of physics, of life, of time, and it can be looked at in many, many abstract ways. Entropy is a system property that expresses the degree of disorder in a system. Here we have, for example, we've got two containers. This is highly ordered. This is highly disordered. If we shake all these particles in here, they will tend to go to this way. Things tend to become more disordered. If you tossed a load of bricks off a truck, what kind of pile of bricks would you expect to produce? A nice ordered like this? Or is it going to be a mess like this? It's more likely to be a mess. There's more ways of it being disordered than there are for it being disordered, than there are for it being in order. So here we have a high degree of order, and then we have a high degree of disorder. So the law of entropy is a natural law of physics. Everything tends to the greatest level of disorder. In the universe, entropy is always increasing. At least it can never decrease. At best, it can stay the same. For example, when heat flows from hot to cold, the heat spreads out. It spreads out into bigger space. There's more way for it to be, so the entropy increases. If entropy decreases in one place, it must mean that it must increase at least by this factor somewhere else. And to give an example of this, if you find a place, if we were able to take all these bricks here and put them into order here, we basically decrease the local entropy. But in order to do this, we have to pick up the bricks, we have to do lots of work, and that will expend a lot more energy elsewhere. So the entropy in the world, in the universe, will increase because you are even if locally you're trying to decrease the entropy. So the law of entropy is a statistical law. Things happen, or in other words, we get disorder because there are more ways for this to happen. The more ways there are for things to happen, the more likely it will happen. And also this is described, as I said, as the arrow of time. Let's take this chessboard. And let's say we have this particle there. How many ways can this particle be on a chessboard? Well, basically 64. If we have two particles, there are many more ways for this to happen. We can have 64 with 2 on each, but you can have 64 for every time that the first particle is in the square. The second one can be on any of the others. So there's 64 plus 64 plus 64 and so on. So the more particles there are, the more energy there is, the more disorder we can have. The more particles, the more ways, the more disorder, the more entropy. But let's have a smaller volume. So we just have a volume of 4 units here. There's only 4 ways for this to happen. If we have this particle here, it's only 4 ways for this to happen. So there's less ways, and there's going to be less disorder, and this is a system which has less entropy. We can increase the entropy, of course, by adding more particles. Here we have an entropy example. This is done with a mathematical equation that we do not need to know, but it serves to illustrate this point. So when we have hot, there's lots of particles there, lots of energy particles, energy units. So we have large disorder, large entropy. Here we have the same volume, but few units of energy. It's more ordered, and there's a small entropy. What happened with these two? Well, basically, the mathematical equation is that the change of entropy is equal to Q, the amount of energy, thermal energy divided by the temperature. What's going to happen eventually is that they're both going to be at the same temperature. They're both going to be roughly around 300 Kelvin. And we'll look at this mathematically. Let's say we transfer 4,000 joules from the hot object to the cold object, in other words, to get this situation, thermolibration. So the entropy change will be 4,000 divided by 400, because this is the original temperature. So we have an entropy change of -10. So this entropy goes down by 10, and this is 4,000 divided by 200. And this is 4,000 divided by 200. So that's another value of +20. So overall, the entropy will increase. So the hot object loses 10 units of entropy. The cool object gains 20 units of entropy. Therefore, entropy increases. Can this happen the other way around? Can we have this, two warm objects of 300 Kelvin, spontaneously going to 400 Kelvin on one side and 200 on the other? That would mean a decrease in entropy. So this cannot happen itself. Another entropy example. When you're heating water, there's the heat. What happens is that the temperature rises, basically because you are supplying thermal energy to the water. As the water is heated, there are more ways for this energy to be arranged inside this container. And if there are more ways, there's going to be more disorder. So entropy will increase. Let's say we have a vessel of boiling water. We're making it boil, but we're not actually increasing the entropy, because the total average kinetic energy per unit particle is going to be the same. So we're heating it. As the water boils, there become fewer particles because they will boil away. Each with the same kinetic energy, because it has a constant temperature when it's boiling. And there will be less space, so it will be more ordered. So therefore, the entropy will be reduced. But you don't get this reduction in entropy for nothing, because these water particles are spreading out. And so in the universe, there's going to be an increase in the amount of entropy. So overall, there'll be more disorder. So we have locally, we have less liquid, so it's going to become more ordered. But this is more than compensated by an increase of entropy elsewhere. State the second law of thermodynamics in terms of entropy changes. Now remember that the second law of thermodynamics says that heat will not go from cold to hot. Heat will go from hot to cold. So in other words, energy spreads out and the entropy will increase. In other words, energy degrades. With a heat pump, what happens here is that how do you manage to get heat to go from cold to hot? In other words, to decrease the entropy, decrease the disorder, increase the order. Well, you have to do work, external work, for that to happen. And that will increase the entropy in the universe by a greater factor. What about a tidy room? How do you tidy your room? It goes from a state of massive disorder to order. Let's say your parents ask you to tidy your room. It goes from a state of, well, in my experience, when I was a child, a huge value of disorder, huge level of entropy, to a moderate level of entropy. It didn't happen by itself, though. I had to do work. I had to pick up the books, I had to pick up the bits and pieces and put them in an ordered state. But in doing that, I expended energy, and that increased the entropy in an ice cube. Here's another example. An ice cube on a warm day, what happens? Well, the block of ice will melt. Here we have maximum order, because it's a highly ordered crystalline structure. We'll go towards a disorder, which is a puddle of water. Maximum entropy. You'd expect that to happen. However, on a very cold day, what happens? It's going to be the opposite. We know that on a very cold day, minus 10 degrees, this puddle of water will make a crystalline structure. This decreases the entropy of the water. How can this be? When the water changes to ice, it becomes much more ordered. It must mean that somewhere else there's going to be a greater disorder. So we end up here locally a smaller entropy, but as you know that when you the latent heat of fusion, when you produce this crystalline structure, a lot of heat will be released to the atmosphere, to the surroundings, and this will increase the overall entropy in the universe.